Nothing in biology makes sense. That's the starting point of the session.
And then we can hit record. Oh, that's the wrong slide. There we go. Right. Hello, everyone. Welcome to session 24 of BGA24. This session is on Omark by Sina and Yanis. Please take it away.
Sure. Hello, everyone. I can share my screen too. Yeah, my name is Sina Majidian, and with Yanis, our colleague, we will talk about OMO and Omark. Yanis and I were a postdoc at the University of Lausanne, and recently either of us moved to another country. So, yeah, we are really happy to present this work and with some hands-on activities. I just sent a few links on the Discord, but we will go through one by one. Just to give some idea what we are talking today, the learning objectives is to we want to know how we can find orthology information for some well-studied species, because for many species we already know quite a lot of information about them, and we will talk about OMA browser. Regarding orthology, we need some other concepts of like orthologous groups and the hierarchical orthologous group. We talk about them too. Then we talk about how we can quickly estimate homology and for some new species that we sequenced. We use a tool called Omark, and which interpret the result. And the main part of the talk is about proteome quality. We use a tool called Omark that Yanis, the team developed. We will discuss how to run it on command line, and there's also a web interface. So we will have 3 sections. For each section, we have some hands-on activities. The first section is on the concept of a hug, hierarchical orthologous groups, and the OMA browser. Then we run OMAmer. Finally, we talk about Omark for general repertoire quality assessment. So during this talk, we have a dedicated website. You can check it here. I can quickly open it too. So on OMA browser, if you click on the link in the help section, we have this OMA Academy. And today we have this BGA, OMA and Omark. So number 5. I already sent the link. We will go through each section and we talk about them. Yes. So it's good to have this link at hand too. So let's talk about orthology and hierarchical orthologous groups. Probably a few of you already are familiar with the concept, but to be on the same page. So we are interested in studying species and how species are related to each other. We try to find regions that are from the same common ancestor, and we call them homologous regions that are regions of common ancestry. And these homologs construct gene families. And these regions are shared among species, but there is an important point here that when we are talking these regions, it's important to know whether they are from a duplication event or a speciation event. For example, here in this gene tree, there was an ancestral gene in an ancestral species. And if we follow their evolutionary history, there was a speciation event here, S1, and then there was another. There was a duplication, we showed it with a star, and then another speciation event here, S2. So we will have these 5 genes. These 2 genes are human. And we want to know whether the relation between genes. We call 2 genes into a species as orthologous if they derive from 1 gene in their last common ancestor. So here, let me show you the same example. We have these 5 genes, and we want to know the relation between different genes. We have this speciation duplication event, sorry, and we have these speciation events S1 and S2. Now, based on the definition, these 2 genes coalesce here. We have this 1 ancestral gene and the speciation event. So these 2 genes are orthologous. On the other hand, this blue gene to this red gene, they are paralogous because they are from a duplication event. Also, this gene compared to this one, if you compare these 2, these are paralogous too. And we can draw a kind of pairwise orthologous relationship between different genes and species. So let me know if there is, we can have this session very interactive. Let us know if you have any questions, either on Discord or here as chat, or we would be happy to like activate your microphone. I guess people can ask their question orally as well. So another concept that is related is that we use a lot in our different studies is hierarchical orthologous groups. These are sets of genes that descend from a common ancestral gene in a given ancestral species. So at each taxonomic level, we can define these, and this creates a kind of nested structure. Consider we have this species tree. We have the mammals speciation here and the tetrapods speciation here. And if we compare this to the gene tree, and when we check the evolutionary history of these 5 genes, based on the definition, for example, consider we are here. At this S2, at the mammals speciation, consider this ancestral species. These 2 genes can be grouped together as one hierarchical orthologous group, one hog. We call them hog 1A. And also here we have S2 speciation event, and these 2 genes are grouped as hog 1B. So these 2 subhogs are at the level of mammals. If we go 1 level deeper at the tetrapods, we can, because there is a 1 speciation event and 1 ancestral species, all of them are grouped together as 1 hog, all these 5. And here we can see this nested structure. Yes, and so this nested structure helps us to work at different levels separately and help us to understand what are the evolutionary events happen over time. Hogs are gene families, and so this approach of hog help us to define them at different taxonomic level. For example, we have the whole gene family, all of these 5, and at each taxonomic level, we have different groups. Maybe Yanis, do you want to add here any information?
Yes. So all in all, like this structure of hierarchical orthologous groups So that's like a way to represent homologous genes that we use a lot in the lab where we both come from in Lausanne. And that's also the basic point of the OMA database. What's cool about that, and that's what Sina mentioned, is that as we define hog at different taxonomic levels, there are representations also, there can be representation of the gene repertoire of the ancestral species. So, because if we say like genes in one hog all come from a common ancestor at this taxonomic level, then we can say there was probably only one gene in this species that gave rise to all the genes in the extant species. And I see my camera is weird.
Yes,
now,
I think yes.
I don't know what happened. What I cut it for now. So yeah, that's help us like model the evolution of all gene families across all species. So this information, then we have it in the HOMA browser. So maybe I can
Sure.
get this my screen shared now. So let me take the scene. It's desktop, and you should see it now.
Yes.
I think to use the same presentation. So we were there. And so that's here we wanted to present you like the interface to the HOMA database that use this org structure and how you can browse this information and understand it, how you can explore all this homology relationship in this framework. So all this data is on the OMA browser website. Here is the links. I think it's also in the Discord. So right now we are around 3,000 genomes from whole life. I think it's 2,000 also prokaryotes, mostly bacteria, and then a few 700, I think, eukaryotes. So a few species with that makes a lot of hierarchical autologous groups. And when you look at hierarchical autologous groups at any level, here is how it looks. So there is always a graphical view that represents the gene family. So here we have a hog with 39 members. So these 39 genes that come from one gene in the common ancestor of primates, according to Omark. And here's a representation of the species tree of all the species that have these genes, and each square here will represent one gene. So if you mouse over any square, you can get the identifier and everything. Here, just a screen, but you can have a whole interactive view. And then you can also explore what happens at each node that leads to, in some species, to 2 genes. So it's probably at some point a duplication event. And if you get your mouse on every node of this tree, you also can see how many genes were there at these taxonomic levels, because you can say it's one gene in the common ancestor primates, but probably at some point in some common ancestor, it got duplicated, which explains this pattern, and all of that can be dynamically explored. So one thing I mentioned about the hog, what it allows us to do is to model also the gene repertoire, the potential gene repertoire of common ancestor species. So here we call that ancestral genomes. Here it's ancestral genome of primates, and you can have a table of each ancestral genes that's here represented by a hog. So every row in this table is what we think, what Homer thinks was one common ancestor, one gene in the common ancestor of this species. And if you click on it, you can explore it and see what it is. You can see there's also a bit of a descriptions of every of these genes. So that's Homer here. It allows you both to explore evolutionary story of any gene families, but also try to understand how these gene repertoires evolve over time. And that's here, that's it for the theory and for the presentation of the concept. So now we have a little undone tutorial on this, where you can use the Omark browser and explore the different data we have. So here's how it works. So I click on it, you'll get on this page, and first you have the first tutorial, so you can read it, and we have a bit of questions, so you can explore the website to answer the question, and you can look at the answer directly by clicking on the little buttons. So all of it, it's made for you, for it to be free for you to explore at your own pace. What we're going to do is leave you some times to get through that. If you have any question, of course, feel free to ask. That's why we are here. And whenever you are done, I think I'll just post something in the Discord, and you can put a hands up as an emoji on the post when you are done, so we can know we can carry on with the rest. So yeah, hopefully it's clear. So I'll stop sharing for now. Maybe one thing we can do before going through that though is also, so we have a Git pod for the next sections. What will be great if it could start the Git pod session already, because there's a bit of downloading to do and it takes some time. So the links to the Git pod, I think, is on the GitHub of the course, and there should be the links also on Discord. So, okay, hopefully it's clear. So feel free to ask any question, to unmute yourself, and we'll stay around.
Yes, I sent the GitHub link here too. Please open this, and because it needs sorry, it needs some time to install the packages. So it helps us to proceed the next step. And on Omark Academy, for the BGA, there are 3 sections. Now we want to work on section 1, the Omark browser and Hawk. And just to emphasize, like we have these 3 sections, but for now we want to only work on the first section, the Omark browser and Hawk. So there are 7 questions. I guess maybe like 5 or 10 minutes should be good.
Yes, and I want to emphasize, so if there's like any things that are not clear in the material, or if you have questions about finding data that are not explained there, you can of course feel free to ask.
We have a question. Okay, yeah, I guess Yanis is answering this.
Okay, I started answering on Discord, but I guess it will be faster to answer by voice. Okay, we have a few questions about the Luca.h5 database. So that's a OMAME database that are provided with the on the Omark browser. So we'll get to Omark a bit later, but I'm still answering these questions. So the question first was how often this database is updated. And so this database, as I said, is completely tied to the release of the Omark browser database. So it has the same number of spaces in it. And yeah, we aim for once a year release at least, but it really depends of the amount of computation we have to do for the updating. And the second question is, why would we use one more specific database? Sorry?
I guess you can go.
Okay. Yes, so why use one more specific database? I'd say the main reason will be to reduce the amount of computer resource you have to allocate to do a search. So in general, it will be only on the context of placing spaces in Omark, a sequence with Omark and not for the Omark application. So since with Omark, you want to find quickly homologs for your species of interest, if you have, say, a plant and you're sure you have only plant sequence in it. So you can use a very plantive that will give you the same result as a eukaryotic database, but will be lighter both in memory usage, in time, and well, any computing resource needed. I'd say Omark is still quite lightweight, so using the Looker database is never really too much of a bother, but that's a way to make it even easier in terms of, well, easier on your computer. That's the main reason.
Hello. I have a question. I'm running the Omark right now in the Git pod, but just a conceptual question in terms of hogs, and does the classifying the hogs consider like ploidy, For example, if I have a, I don't know, a tetraploid or a hexaploid or something, and the Omark output includes a high number of duplicates, how do I know that the duplicates are true compared to the, I guess, the original species hogs that it's going back to at the, I guess, point of duplication? Or I'm not sure if I'm wording that correctly, but you could comment on kind of ploidy and hogs. That'd be helpful.
Yeah, sure. So I can answer that. I'd say that the main, the first answer I can give is it's not something Omark can really do. Is being sure like a duplication is real or not is really hard. So if you do see a lot of duplicate, I'd say this will be the expected state, and then giving you the number of copies is not something it does naturally. I think if you beta depth, you could look into the files that Omark output, and especially Omark, to see like for any hogs, I mean, what's the number of copy, and if so, what's something Omark can do, but it's really dependent on the species we have, is it will classify the duplication within expected and unexpected. What it means is if Omark can identify that it's maps to a duplication node after the ancestral species it considers as a reference species. So if it sees it's actually mapping to a duplicated non-duplication, so let's say we have another species that's come from this whole genome duplication too, it will classify most of the duplication as expected, and you can say that it does map to one of the non-duplication. Otherwise, it will classify it as unexpected, which doesn't mean it's wrong. It's just we don't have that in our reference database. That's what Omark can say. But I say it sometimes lacks a resolution to be more precise. And then if you really want to look into it, you'll need to look at how every gene is classified, what are the ones that are classified the same gene family, and I don't know, and what else you can do. But it's really hard then to say when really a duplication should be wrong or not at this point.
So the function where you specify isoforms is only searching, I guess, the best scoring isoform, and it's marking them as genes, but not really using them necessarily to scan for duplicates. Is that?
Yeah, that's right. So the
Right.
isoforms is mostly for protein isoforms of the same gene. So it's what we do then is we will select the best scoring one, yes, as you said. So this way it's not accounted. It shouldn't introduce some false bad quality sequence just because it doesn't select the good isoforms, but it's not used at all for anything that were duplicates. Yeah.
Thank you.
Okay, I guess these are quite good and advanced questions, but for people who are new to this workshop and this field, we will go step by step, so don't worry. Yes, so maybe I guess now, Yanis, do you want to go through the answers for the interest of time? Muted.
I see. Finally, my camera is back. I did. Okay. Maybe not. Okay, I start trying. Yes, so I'll share my screen really fast. So you did have the answer for the question, so maybe we'll don't go into details for things, but I hope you didn't have any trouble finding the information. So the first part of the question are on the on the species content of OMA. So what we wanted to help you with here is find what are the species we have in the database. So if you have your species in interest in there, you will find a lot of orthology information about it. And you will know also this is used for any of the other software we'll talk after. So these 3,000 full genomes are the one used for Omark and for Omark too. So you can find the species information in there. So here you have a little sunburst that gives you the taxonomic distribution of the species. So that's where you can find information, for example, on the what I call the number of mammals. So if we go up to, so it's a bit slow, but let's go deeper. And Utah. Yeah, we go to mammals. Yeah, we can see as a mammalia, and on the little tooltip on the side, you can see the 78. So you can look at the distribution of the number of species, and you can also look for any taxon in here to get a list of species. So you write the taxon, you specify you're looking for it, and you'll find the information here about this taxonomic level, the number of species that are present in it, and then the last update of the data in OMA. So we try to update most of them quite regularly, but if you feel like your proteome of interest is not updated often enough, you can also, of course, write to us. So I don't remember, I think it's a contact link. You can ask for adding of new species and also for updating of some genomes. But let's go then to the hog structure. So here we go to the P53 genes. So the page you see here are the genes with the pairwise orthologs, but what we're interested in here are the hogs. And this is what we saw, what we showed earlier about the hogs. So you can see this is genes defined, hogs defined at the level of uterostomy. So this was one gene in the uterostomy common ancestor. And then you find it in a lot of species in 1 or 2 copies. If you go in the internal notes, you can see, like, for example, on here in Daniel area, you can see these 2 copies, and that shows there's a duplication that happened. Yeah, that will be at the level of Uterostopomorpha. And if you looked at the one with the most copies, I think it was elephant, and it was shown here, Loxodonta africana, with quite a lot of copies. So if it's changed a bit too much to your liking, you can also freeze the view so it doesn't change. And here you can find, like, so all, like, the whole evolutionary history of the family, try to understand where duplication occurred, and you'll find the number of the genes in there, of the hog in here. So here we are at the level of mRNA, but we can click on that to get more. And you'll have all the genes, and then you can export it if you want, for example, as a FASTA sequence for more phylogenomics kind of analysis. And well, there's a lot of other things in OMA. There's, we hope, some enough documentation of the website if you want to go deeper, for example, in the synteny, look at the synteny, get the alignment of the sequence, look at the what we thought was ancestral function of the genes. So there's quite a lot of options. We don't really have time to go through all of it, but I hope it helps you answer all these different things, and that you found the same answer as we put here. For the next part, so we wanted to go in the next section. So here we show, we looked at how to, or maybe there's more question. I'm just going to,
Yeah.
Is there more question about the?
I think there was one question on There was one question on Discord, but I think it's solved. But
Okay, with question 3. Okay, so maybe I went a bit fast.
is it solved or?
Yeah, I think you gave the right answer. So this was a 2-part where you could obtain the information. To get the info. So either yes, you go to explore species related information, or you can, in this case, Papilio macaron, you can just get the name, right, tax species, because it's a species. It will lead you to this information. And here you have quite a lot of things, but these in part like the DB release, where you have all the information about what the identifier of the release, the date, it was added to the database, and the link to more information. So hopefully that answers the question.
Yes. And for the search part, maybe we have like, it's a bit different on the search part. Sometimes you need to use a space on the keyboard when you are writing to make it complete. And you could also select what kind of information you are searching for, like the tax ID, the gene name.
Yes.
When you start writing, you can select.
That's right. Yeah, I bit used to it, so I didn't demonstrate. But yeah, that's how it works. Is often you will type something, and then once you have done typing, you press space to validate, and here you can look precise, be more precise about what you're looking for, and depending on what you're looking for, that's what the website will look for. Okay. You had all the information. That's great. Okay, so now for the next part. So here we show how you can find existing information about what we pre-computed orthology, but often you'll want to work with species that are not in the database. So that's where we use Omark. So Omark is a software we developed also in the lab that used for fast sequence placement into existing hierarchical orthologous groups. So it looks at the existing gene families we have in the Omark database, and it will try placing the sequence into it based on the KML contents of the sequence. So there's no alignment done, it's all alignment free, so that's why it can be a bit faster than the usual orthology method, but often it will give you satisfying results in terms of placement. So the paper about Omark is available. I don't remember which journal, but you can look for it online. There's also the GitHub. And here is how it works. So you start with a proteome. So let's say you have the proteins, the protein coding genes of your genome that you translated into proteins. And you want to know what are the different orthologous groups that correspond to these proteins. So what Omark will place first them into rootogs, so the highest level hierarchical orthologous groups. So it places every of these sequence into it. And then within the hierarchical orthologous groups, it will also try to place it to the subfamily it belongs to. So after which duplication and at which taxonomic level this species should belong. So it's quite precise. Sometimes it can make small mistakes, but you will be able to catch them just based on the taxonomic level it gives you. So what Omark does is cut the sequence into k-mers. So often in the classical setting is 6 mers. So word of 6 amino acid letters. So that's it. Let's say you have this sequence. So that's what Omark is doing, is get every 6-letter word in this sequence. And then based on this KML content, it'll try to look for hogs that are similar KML contents, and also look at the different subhogs that have this KML content. And in this case, like here we have 5 KMLs, 3 that are in common for all the whole root hog. So that will say it plays into these gene families. Then you have 1 that goes into one of the subfamilies and the other going to is specific to the other subfamilies. So given this information, what Omark will do is say, okay, I'm sure this is the correct root hog for the placement, but I have no more proof that it should be this or this subfamilies because we have the same number of kmers in common. So we'll place it into the root level hog. So that's what it does, looking at the kmer content and placing into hierarchical orthologous groups. So that's what you need to run Omark is your proteome, a database that we call the Omark database in the HDF5 format, and that's available on the Omark website. Omark will take both of them and do the placement, and it will give you a text file where for each sequence, you'll have the hogs it was mapped to, and a bit of more information about the placement and why, like what the statistics of it and how many kmers were in common and the length of the different sequences. So there's a lot of information, but mostly it will give you for each sequence one placement. So here is a command line, the classical command line you use, Omark spaced search. You give the query proteome, the database, and where you want the outputs to be, and it will just work in a few minutes. Place all your sequences into hierarchical orthologous groups. And that's what we are going to work on this time. So everything here will be done on Gitpod. So first we'll ask you to find the command line, but you'll be able to use it. Make sure when you run Omark to specify to use 4 threads to make it a bit faster, because given the capacity of the Gitpod, it can take 10 minutes if we don't use a full thread. And while it's running, you can also look at the expected outputs files that we provide in the Gitpod as well to start working on the output. So yeah, that's here for the Omark. If there's something not clear, let me know. And of course, so here is section 2 placements with Omark, and here we give the indication about what you should do. So what we're going to do is place the sequences of one proteome, is a narwhal, monodon monoceros, that's not in the Omark database, and see what placement it does and how we can make use of this information. Okay, so now give you, let's say, 10 to 20 minutes to go through it. And of course, again, don't hesitate to intervene if you have any question. Stop sharing for now.
So about Gitpod, when you click on the link and click on continue, you have your session. It takes like 4 or 5 minutes to download the database and install all the packages. Then you have the control to start writing the command line. But if you are at each step and you have any question, just let us know. Because the first question of this section to ask you to run Omark, that's why we need this Gitpod. or if you already install it in your system, but it takes more time.
So one thing I just wanted to show, just to make sure, to reassure you if you're at this point and you're asking questions. Once you manage to run Omark, so it will give you this screen. So first it gives you like all the different information about the program. It takes, I'd say, around 1 minute to do the camera indexing. This is normal. Then after that, you'll have a progress bar, and for a bit of time, you'll say it will look like it's not progressing. So giving you a progress of 0. This is completely normal, so no problem if you having that. It just will give you an estimate of time once it's go through 10,000 sequences, which take a few minutes. So no worries if you are at this stage and you don't have and you don't see this information for now. I'm just keeping this to show you what it looks like. So what we noticed is on KitPod is a bit slower than we are used to. So it depends really of the machine you're using and the capacities. And it will take you for one proteome anytime for a few minutes to say dozen of minutes, depending on the computer. But normally it should still be faster than anything else you could do for homology charging. So yeah, that's what I mentioned. So at some point you'll go to a search bar, and for at least a few minutes you'll have 0 queries. This is completely normal. It will update only after 10,000. So none of this is weird, and it's progressing if you have this screen. Yeah, I just wanted to mention I wrote like a little sentence on Discord. So when you are done with this section, whenever you think you saw everything, you can just put a little emoji. It will help us knowing like, like to make sure we're not getting too fast with going through the answers. Well, yeah. So when we have like a few more hands, we'll carry on with the answers. Okay, so if guess you can't use grep, it's a bit harder. Okay, anyway, you have to count these lines, you'll find that it was just to show you like how it looks like when we don't have any hits in the files. It's mostly a lot of NA, which indicate there's no results. Yes, so maybe I see there's a few hands now, so I can start getting to the answer. Screen sharing. Okay. Yes, so the first question was about finding the the comments. Here we give the answer, but you probably found it by yourself. The only things we added here is a minus T4. So here it's to indicate the number of threads to use by default. Well, to use when running. By default, it will only use one, so it will be a bit slower. But here it was to make things a bit faster here. We use the 4. And then the first question is about looking at the output of Omark, and I here give a bit more precision. So here, if we look at the Git pod, and you probably have something similar, is how it looks like, or the output file look like. So you have a few lines on top, just give you some information about your query. In particular, it will give you the database information and what's the date, like what's Omark database was using. So here we're using the latest one. It's using the Looker database. And here we can get back to what we were saying a bit earlier. So the database will give you like how much of the Omark database Omark will query to find the best hogs for your sequence. So we have the Looker database, that's basically all the spaces in Omark that are being used. So that's the one we're using. But we also share a few smaller ones. That's the Metazoa, Viridiplanti, and Primates database. And as I was telling you earlier, it really depends on what you want to do with this database. If your goal is to find homologs for only to find homologs for your species of interest, you're sure there's not anything looking like horizontal gene transfer or contamination, then let's say you have primates, it will be much more efficient to place in the primates database because it's much lighter and it will also be much faster. So that's the main reason why you should use one of the smallest one, but it's often okay to use a Looker database because even then it's not that slow. And here that's how the output looks like. So it's a tabular file. And you have a bit of information here. The most important information, I'd say, as a 4 first column. So it gives you the identifier of your sequence, the hog ID, the hog in which it was placed. So if it's a top-level hog, it will look like that. If it's a nested hogs, it will give you all the information about the nesting. And if you take any of these identifier and go into the Omark database, you'll find all the other sequence that belong to the same hierarchical orthologous groups. So that's a way to find all the homologs for any of your sequence of interest. And you can also automatize it. So if your goal is to make to find all the homologs for all of the sequence to do anything like phylogenomics analysis. So it's easy to find the homologous sequence from that. Okay, yeah, I see now. I shared a bit wider screen where we can see the different parts a bit easier. The third information is the level. So as a level at which the hierarchical orthologous group is defined. So this is the same. It's not necessarily giving you the best, like the deeper node that corresponds to your species, but where the latest duplication we can find happened at. And here, the next one is a family P, and it's a negative log of the p-value of the placements. So the p-value is the chance that we have as many k-mers in common with these hierarchical orthologous groups if you were to draw k-mers at random from the database. So knowing the frequency of the k-mers. So it gives you an estimate on how likely it is to be by chance, unlikely it is to be. So since it's a minus logarithm, even small value, so above 10, is already quite low in terms of probability, and 1,000 is, it's basically 0 chance that it happened by chance. So you can be confident of your hits if you get p-value in this order. Then there's some information about the number of KMLs in common. So this is family count. It's normalized by the length of your sequence. It's the same things for subfamilies. Is this information is to get a bit more information about the placement, which is not that important often. And at the end of the line, here you will have, in particular, the size of the proteins in the hierarchical orthologous groups. And so this is a subfamily median seq length, and you will have the query sequence length. So these are kind of useful because it can help you compare the sequence of your proteome with the homologous sequence we find. And if there is a big discrepancy, then maybe there's some fragmentation or gene model quality issue. So yeah, all this information you can find in more details on the Omark GitHub, so what each of these columns means, but it was a bit to help you going through that. Then let me go back to the question. So here you probably saw something as us. So if we look at for this sequence in particular, so if I look for it in my file, and then here I'm using grep. Yeah, I can see it here, and you see here this is the family score that's really high. So it gives you the confidence that it's well placed. And there's also a subfamily score, give you the number of KMN common with the subfamily, and it's close to 1, which also gives you confidence in the placement. So that's how you evaluate the placement. As I said, for any of the hogs, you can then go into the Omark database and find the information about this. And yeah, if there is no assignment, you'll see a lot of NA appearing in your file. It's when there is no clear homologs for your sequence, which may indicate that it's some specific sequence of your species, or maybe some errors in the placement. So that's what one of these lines look like in this case. Yeah, so I think we went through that. So really this Omark tool is a way for you to quickly get homologous sequence for any species. And here, I guess.
Yeah, just one more point to add here is that once we have this mapping of the protein to the hog, we can get some information from the Omark browser for each of the hog for the input sequence. So I add an example on the Discord.
Thank you, Sina. Yes, so this is one way you could get really fast homology placements for your proteome of interest. If you're interested in getting a bit more detailed orthology and for more one-one species, we also have a tool for that we don't present today, but that Sina developed, that's called FastOmar. So it may be of interest to you if you're interested in fast homology calling. So FastOmar also use Omark as a first step, but also do a bit more better resolution of orthology after that. So this is this website if you're interested in follow FastOmar, and there's a very good documentation of the GitHub. So I just wanted to mention that before going on for the next part. Yeah, so is there any question about the Omark part? I see someone is typing in Discord.
Probably it's me, but
okay. Maybe it's good then. Hide the information about FastOmar. Yes, so the next part of this session, now it's about Omark. So Omark, contrary to what we saw before, is not about orthology inference, but it's about using results of this homology information to evaluate the quality of a proteome. So the resulting proteins that you may get from gene annotation. So gene annotation will structurally annotate the genes. You will get a coding sequence that then you can translate into proteins, and that's the resulting proteomes that we can evaluate with Omark. So Omark is thought as a way to evaluate coding in gene repertoires or proteomes. So here we mean set of coding genes annotated on a given genome sequence, and that are often available on databases as proteomes. So as you may know, these proteomes that exist for a lot of species, and they have a diverse quality. So they might sometimes be missing genes, they can be fragmented genes, they can be inclusion of non-coding regions as coding genes, or they can be contamination from other species. And you might have a bit of all of that on any given proteomes. And the issue with that is then if you use them for any analysis after that, there might be bias that get induced by included these erroneous genes. And we decided to design Omark because we thought there was a lack of tool to detect all of these issues at once. So there were tools that were able to detect some of them, but we didn't have like a real suite of software that could try to evaluate quality on all these axes. And so that's what we're trying to do with Omark. So what Omark does is really using Omark placements to obtain to get a global quality evaluation of the proteome. And it's so what you need to do to run Omark is first run Omark to get the placement, as we just did, and then just run the Omark tool, as you'll see how to do in the next tutorial. So first thing Omark does is it needs to define an ancestral lineage to which to compare the proteomes. So everything will be compared to a clade of interest. And the question we'll be asking every time is this proteome in line with what we know about these clades in terms of gene repertoire? So Omark defines ancestral lineage as the last ancestor clades that contains your proteome of interest and that have at least 5 representatives in the Omark database. And this ancestral lineage, either you can select it yourself on the command line, but often you can just let Omark decide, given on the placements you give to it. So you give it Omark placements, and often Omark will be able to find itself what's the lineage of interest, what ancestral lineage to use. And this ancestral lineage will be used to define a set of conserved ancestral genes. So that are gene families that we thought existed at this ancestral level. So genes, for example, that we thought were existed in the common ancestor of primates, if we're talking about humans. And we want these genes to be present in at least still 80% of the species of these clades. And we will use that for completeness assessment. It's quite similar to BlueScore in that sense. So that's what Omark does. It takes this concept ancestral genes, and by comparing it to the proteome, it will tell you like whether some of these genes are missing or if they are present and in how many copies we find it. Contrary to BlueScore, that you may know, here we're not using single copy orthologous genes, so we don't necessarily expect a duplicated proportion of 0. But if you compare the duplicated proportion to non-species and you're quite certain your proteome is not polyploid, then having more duplicate than other species might be indicative of quality issues too. So this is the first part about completeness. The second thing that's really specific to Omark is consistency evaluations. And for that, it uses a broader set of genes. These are the lineage consistent genes. There are the gene families for which we know there's representative, at least one representative in the clade of interest. So gene families we know exist in the clade of interest. And we use this lineage to evaluate what we call the taxonomic consistency of the genes. So to make it simple, if the genes we find in new proteome are also known to exist in new clade of interest, it's consistent with our knowledge of these clades, and we call these genes consistent. If we find genes that exist but in other species, then it may be either contamination, and Omark will call contamination if we see there's multiple genes, quite a high number of genes that always map to the same clades, but not new clade of interest, called it contamination. If Omark cannot find any pattern in this placement in other clades, it will call the placement inconsistent. So inconsistent placement, things that are placed in other species, but there is no observable patterns. There might be actual good protein coding genes, but that are just not known in the proteome of reference. So it's not necessarily bad quality. It may be in the case, for example, of low complexity reagents. And finally, you have all the genes that are not placed in any family. So genes for which we can't find homologs. So either they are genes really like specific to your species of interest, or there are genes that are wrong. Of course, Omark won't tell you any of that, but if you see, for example, your proteome as much more unknown than its closest species, then it may just be indicative of quality issues. And there is no homology because this protein actually does not exist. So this is what Omark gives you. And here is an example I gave you for an actual proteome. This is a big-headed turtle proteome. So we use as ancestral clades Archelosoya clades. And for this, there's 10,000 conserved hogs. And for these proteomes, we see that we find 92% of all these hogs. So this proteome is mostly complete, but it still have 8% missing. And if you were to compare it to other turtle species, you'll see it's more than other turtle species. So there's some gene missing for sure. It's not that bad, but it's a bit, there is some gene missing, so it's good to know. Second thing is then we look at all the genes in this proteome. So it's 21,000 in this species. And you can see 82% of these are consistent with what's known. But Omark does detect a bit of contaminations, and it will tell you it's contamination from a propionobacteria. So there's some bacterial sequence in this protein, so probably a contamination at the proteome level. It could also be horizontal gene transfer, but in this case, we're quite certain it's probably bacteria. And then this 14% of genes that are unknown, and if we compare it to close species, actually it's much more than expected. So there's a bunch of these proteins we think are actually not actual protein coding genes. So this is the first information you can get from that. The second information that I didn't mention now, it's what Omark will give you. Also, it's a rough estimate of how good the gene models are. So some genes can be consistent taxonomically, so we know they exist, but they can have some gene model difference, in which case we will call these genes partial mappings, which means there's part of the sequence that do not correspond to these hierarchical autologous groups. So part of this sequence that have not this homology, so maybe errors in the gene models. And also, it will tell you when there is fragments. So this is a right line here, and that are genes that are less than, I think, 80%. Yeah, that are the size difference with the known sequence in these homologous genes that are less than, I think, I don't remember, I think it's maybe 50%, less than 50% of the expected size. And it will call that as fragments. And you can see here there's some gene model issues in this protein. So this is what Omark tells you. And now here, in the last section of this tutorial, then you run Omark and you see how to interpret these results. So you will use the Omark file you just generated and just run Omark on it, and then look at how to interpret the different the statistics it gives you. So we'll do it on the command line, then we'll see really quickly how to do it on the website too, and the web server, and to compare it to other closed spaces. So yeah, I'll leave you to that. So Omark also takes some time to run. It will take you maybe, I'd say, between 5 and 10 minutes to complete. And so I'll leave you to it. And of course, if you have any question about the presentation or about the tutorial, don't hesitate to ask. Yeah, maybe one thing I'll mention, if you're not on Gitpod, because on Gitpod we set it up so all that Omark is installed directly through Python. So Omark can be installed either through PyPy, so with pip install Omark. I think we have it written in the tutorial. You can also install it with Conda, so it's on BioConda. Conda install Omark will also install it directly. Omark and all its dependencies, so you can have Omark directly like that too. Second things I want to mention is that with Omark, I mentioned you can use different database. For Omark, we like to recommend using always a Looker database, because that's the only way you can detect contamination. Well, for example, if you don't have Looker and you don't have the bacteria in it, then you'll miss all bacterial contamination. Yeah, and maybe some things I always forget to make clear. So Omark is really have been developed, and I recommend using it mostly on eukaryotic proteins. So it's really designed to evaluate the quality of protein coding change annotation on eukaryotes, and because that's I'd say it's easier for us in a way, because in eukaryotes, barring some known exceptions, horizontal gene transfer is not that much of the rules. So it's easier to call contamination and also to get good consistency estimation. And also, we really thought about designing it for eukaryotes, because we see that for gene models in particular, eukaryotes suffer a bit more of the problem of bad delineation because of all this exon intron structure that really make it hard to find exactly what's a gene and what are the part of the gene that are coding.
So I also put the link to the expected result for both Omark and Omamer. If your Gitpod has a problem or you want to see the final result, and then based on this result, we can answer the question.
So I noticed in the presentation I didn't give the reference to the publication and to the GitHub. So all of it, so you can find more details on both these links I just put in the Discord. Okay. We have a question. Yes, I don't know. 94% are consistent, 10% was partially, 13.5% are fragmented. Yes, indeed. So true. Even though that's the goal of this this question. So we see indeed that most of them can be mapped to an existing gene families, but in terms of gene structure, there seems to be worse, and indeed it reduces the proportion of the genomes that are probably of high quality. And one thing I can mention is Omark never will give you a result of 0% in partial hits of fragments because it's always reference based. So if there's bias in the reference, then it will. Okay. Thank you. Thank you, Maria. Yes, so even if it gives you a few percent of partial plasmon fragments, it may be biased in the reference and maybe other things. So 0% is not realistic, but still 13% is quite high. Really what we recommend with Omark always, because the quality of the reference would always depend on the clades, is to always go back to other results for the same clades and see if it's in line with what are the best annotation. If it's in line with the best annotation, it's not doesn't mean it's super good, but it's at least the best we can do for now. If it's much worse than other things that are available, it's probably actual mistakes. Oh, so is there a way to plot all of those that are partially fragmented? Indeed, there is a way. So I was going to get over it later, but actually I can do it now. Let me share my screen again. Share screen. So yes, so that's one of the files that's provided by Omark. So by default, it won't give you the sequence, but it will give you the identifier. Of course, I didn't run it myself this time. In the expected outputs. So yes, so the extension will be random, but you have a .ump file in there, and that's actually the results as all the categories in the consistency results. Well, I should rename it now, but it's careful that people are worrying on this extension, so I decided to keep it this way. And in these things here, you can it's basically structured this way. You always have a header that gives you the category and then the identifier. So if you're looking for fragments, you'll have consistent fragments first, and you have a list of genes, and then you'll have inconsistent fragment, contamination fragments. So all the different categories. There's no one fragment category, but just looking at using the IDA underscore fragments, you will get the IDs. And you have the same things for partial mapping, and I think the keyword here is partial. So it's a UMP file, and hopefully it's easy to parse. Yeah, so it's the same, but with partial. And so you just need to look at the header and then just get the list of genes that are below it. Yeah, so I hope it answers the question. Oh, yes, great. One thing I can mention too about running Omark is there's one option to run it to give it the proteome file when running it. It's not the default option, but it's called OG faster, so -OF. What you get when you provide the proteome faster file is it will generate a bit more files where they're also classified by categories. And you can then get all the files, the sequence that are mapped to a given species when there's contamination, for example. I think you can get all the consistent, all the inconsistent, you can get all the fragments as a faster file. So I don't recommend it by default because it's just to generate subset of the FASTA file, so it can be quite big if you do it at scale, but that's something you can do. Okay, so again, I put on the Discord a little header, like to raise your hand if you are done. So we have still time, don't rush it. But once I have a few more hands, I also get through the results. Okay, so I think we can proceed. I see a few hands raised. Now, so I share my screen again. We'll get through the different questions. Yes, so this part was a bit longer than the other, but So here, so to run a Omark, you will see the command, it's here. So this is simple as giving the database. So always look at database, hopefully the latest one you can find, because there is more spaces. And the more spaces you'll use, I'd say the better the resolution of the results will be. And yes, so you can give the query, the OMAME file with -f and the output directory. So it will create a new directory with -o. Here we put -v, so you can also follow what's happening. And after the results, so you can already look by the outputs Omark gives you, it will already give you information about what it's doing, but you can also look into the file. So let me get back to the terminal. So all this information about what happened, what Omark did, is given in 2 files with a point sum file. So it's a text file that summarizes the results. But this one is really meant to be machine readable. So all the information it has here, but they are not necessarily easy to read by humans, but it's good if you want to parse the results later on. You can use these files. And here you have the bit more complete file where it gives you a human readable file. All the information about what it's doing or the sets of genes Omark is using are defined, and how to interpret the results. So you can see here, so for the narwhal, the clade used was the Artiodactyla, and we have 13,000 concept hogs. And this is a completeness results. So with 83% single copy genes, 9% duplicate. This is what I was telling you earlier about unexpected and expected. So we have most of them that are not expected to have duplicated in this clade. And then we have 7% missing, so not fully complete. 7%, yeah, so this is not a fully complete proteome. And then you'll have the results about the consistency, and always it will give you the taxonomy consistency with, for this, so always a total, then what part of the consistencies is consisting of fragments and partial hits. So here you have 20% of the 90, 22% of the 94% of consistence have structural issue. Then you will have some information about inconsistence, no contaminants, thankfully, and then 2% of unknown. And you did notice that this unknown number is corresponding to what was not mapped before in the OMAME file, because that's how Omark get this information. And there is also species composition part. This is mainly useful when you have contamination, because it will tell you what clade it is. So this is how to read it. Of course, Omark will also always give you also PDF file and a PNG files that will summarize the results in figures. That's exactly the same as I showed you before, and that shows the same information just graphically. And so here we can see, this is not the one we were looking at, this is the one we were looking at. And you see, again, proportion of missing with some duplicates, quite a lot of fragments, bit of partial mapping, but really quite a lot of genes that have structural issues, even though most of them are consistent. So that's how you interpret the results. You can, of course, use this PNG file then to illustrate it. And the other things I can mention about these files that are here. So we talked about these two, sum and summary.txt. PDF, PNG, there's the information about there are the pictures. The tax file is not always really useful, but it's really giving you information about what Omark did for the placements. So you have two things. You have sampled and closest. Closest is the clade Omark was able to identify from the placements. So it's looked at the placements in Omama, and it says this is most likely a cetacea, a species that belong to these clades. And the sample clade is a clade that then Omark used as a reference clades. Most often because we don't have enough, more than 5 species in Omark for this cetacea clade, so we use Artiodactyl. So there's not a lot of information, but that's what it tells you. And then, this .ump file. So this is a category file for the consistency, as we looked at it earlier. And there is a UMQ file that gives you some information, but for the missing, the completeness assessments, and rather than giving you gene ID here, it gives you hogs ID. So it tells you which hog were found in a single copy, which were found in a duplicated copy, etc., etc. So that's how to look at the results. And I hope it answers all the questions you may have on this. If you have any question on this part, you can interrupt me. So yeah, this is all the information you could find. Consistency assessment. So yeah, for the gene structure, indeed, as I said earlier, having this high number of issues in terms of partial placement fragments, probably a really quality issue in terms of gene structure, and mostly there's a lot of fragments. And yes, then you can look up the fragmented proteins in the UMP file. And if you look at it in the OMAMA file, you'll see that actually what's happening is the protein in this hog are 800 amino acid long. So that's, maybe I won't do it here. You can grab this in the OMAMA file. And there's only the protein that was placed into is only 344 amino acid long. So it's clearly a fragment. And actually, if you look at that, you'll find that this hog is also mapped to another protein that is 500 amino acid longs, and both together they make more than 800 amino acid longs. So they are both fragments of the same proteins. And Omark will report them both as duplicated, because we find it in 2 times, and as fragments. So that's what's happening behind the hood. The last things we use is then doing the same with what we call a splice file. So really a splice file is a mapping of gene to proteins, all the protein isoform for single genes. And as I guess we discussed earlier, is mostly used for Omark to only choose one of the splice variants, and the one that structurally corresponds most to our homology data. So it's not considered as a structural issue because of the just because it's a splice variant. And it will choose one, the best matching, and will only use this one for anything else. And here, so that was the last question. If you use this second proteome that's from a different source for the same species, you will see that it's both nearly fully complete and nearly fully consistent. So there is a bit of consistency issue. And as I said earlier, it's probably not necessarily errors in the gene model. It's just might be that there's bias in our reference data, or for some reason, these species have bona fide gene structure issue. But the fact that it's much lower than before means that the first proteome had really strong quality issue in terms of gene structure. And the same for completeness. We don't necessarily expect 100% because the gene we selected are not present in 100 of the species of the clades, but it should be close to 100%. And that's what you can say by comparing these two proteomes of the same species. One is clearly a better quality than the other. So that's on the part on this command line part. And finally, I just wanted to mention the website. So you probably went through that already. So our website, the Omark website, is a place where you can submit genomes. So you can submit sequence and splice files and some information. It will run Omark for you behind the hood and then get you access to the data either publicly or if you sign up for an account for your own account. And all the things, the proteomes that you will have uploaded will appear in this list of proteomes. So to precise here, we have all these proteomes you see here, therefore is your conjugalis, and you'll see that we have proteomes from UniProt, Ensemble, and NCBI, and all of this was computed in June 2024. So it's a few months, it's data from a few months earlier than now. But we try to also update it every, I'd say, 6 months is my goal. So you can expect a new update in December or January. And you have proteomes from UniProt, reference proteomes, Ensemble, and NCBI for now. We can think about adding more species. Of course, it will depend on what request phase. And here you can look for any species in this search bar, but you can also look at the data for any taxa. So it's all, it fills itself up. So there is a lot of species, so it can take some time. I think for now we have a few thousands proteome in total. But if you're looking at one specific clade, let's say Cetacea, to stay in terms with the tutorial, you'll see Cetacean proteomes. So you have the NCBI taxonomy to see the relationship between them. You have the name, so here it's a bit cut off, but if you put your cursor on it, you will see the full name plus the source for which it was taken as the identifier. So this is giving you this information. And if you don't want to show things from one database, you can decide to opt out, and it will only show you what you want. So either one of the 3 source database or unverified as any public user provided proteomes. So anything that was provided by our users and that we didn't choose to include ourselves. And here you can see for the cetaceans that most of the proteomes are really highly complete and highly consistent. You can see now the different monod and monoceros proteomes. With this one we had before, but clearly compared to the other, either both a bit more incomplete, but also more fragmented and with more issue in the gene structure. You have a few proteomes that have a lot of missing proteomes and a lot of fragments. Probably the genome itself was fragmented, which can explain these results. And the nice things about that, so if you're interested in the quality of your proteome, one thing we always recommend is then you can go in the website and look for your clade of interest and see how your results compare to that. And you then can form your opinion on whether there's clearly a quality issue. It's also that it's hard to get good estimate of quality for this clade. That's it. And the last things, so at some point I did ask you, and we don't see it here a lot because my screen is not that big, but I ask you to look at the Visceta cadence here from Ensemble, and what you probably noticed, it's really thin here. There's a little orange bar, and there is contamination in these cetaceans. And if you look here on the list of contaminants, you'll see it's the Sarcosis TD sequences. So you have proteins that are from a eukaryotic parasites. That probably was contaminating these specimens, and that then got included in the genomes and translated as proteins. And these clearly contaminations. Even though it's not a lot of proteins, 71 according to Omark. So yeah, that's the things I wanted to explore here. We have, yes, some only eukaryotic proteins there, but quite a wide selections. If the protein you're interested in is not there, you can submit it and see how it compares to the rest. Otherwise, we try to keep that updated. We saw, since we started doing that, we saw like actually there's really good iterative improvement from one version to another of either ensemble and CBI UniProt. All of them are often getting better. And so this data is always reflecting a certain point of time. So you can also see if something has changed in the meantime. Okay, so yes, I think I'm done. So thank you, Sam, also for participating. If you have any more questions here, well, I see actually a lot of people already left. But if you have more questions, you can ask. You can ask on Discord or here. And we'll probably still monitor the Discord for a bit of time.
Yeah, and feel free to email us later if you have any question. If you want to install packages on your own system, we would be happy to help.
Cool. Thank you very much. It's a very cool bit of kit. We've started using it in the Darwin Tree of Life project. So hopefully the genomes that we're putting out should be improved by the work you guys are doing, and we'll go full circle at some point.
Yeah, that's really is a really big hope that the genomes we have actually keep improving, so that then we get even better assessments, because that's, I think, one of our limitations still for now is reference genomes.
Yeah.
Are not always the best.
Yeah, and once we've got talks ongoing with people from Ensemble as well to help improve it on that bit as well. So hopefully in the future you'll have a lot more high quality stuff to get through. Yeah, awesome talk, guys.
Cool.
Thank you very much.
Thank you, guys. Thank you for organizing.
Thank you. Yeah, thank you for organizing also. Yeah.
Cool. Thank
Lots
you.
of work.
It is a lot of work. Yeah, we'll see you all in